So like regular languages, we will now prove some closure properties of context-free languages. And we will see that the CFLs do not have as many closure properties. So we will prove that CFLs are not closed under inversion or intersection. But let us prove the other properties. So first we take this closure under union and concatenation. So if L1 and L2 are CFLs, then their union and concatenations are also CFLs. So to prove that, let's first consider two CFGs corresponding to this L1 and L2. So let's say the CFGs are this G1 and G2, and they have this start symbol S1 and S2. And without loss of generality, we assume that their variables are disjoint. So even if you have some overlap initially, you can just rename the variable, right? So the name of the variables doesn't matter for the language, right? You ultimately have a derivation from the start symbol to the terminals, and even the start symbol and all other variables, you can just rename them by any other name. That doesn't change the language. So we can, without loss of generality, assume that. Okay, so once we have this, let's consider this grammar. And what is this grammar? So it takes all the variables of the both grammar. It introduces one more symbol, one more variable, which is a start symbol of this grammar. Okay, so we are introducing a new start symbol. That is the only new symbol that we are introducing. Otherwise, we are taking the variables of this V1 and V2. The input alphabet is same for all three languages. So here these are same because we are going to make union or concatenation. So this sigma is fine here. And the productions are also, you see that it takes all the production from here and it takes all the production from here. On top of that, it just introduces another production. So this is just two productions. Okay, just this line in the production. So use this. Now, why does this generate this union of L1 and L2? So this is clear from here because, see, what is L of this G? All the strings which you can derive from this start symbol S, right? And how can you derive something from this start symbol? So you see that this S only has these two productions. So when you start with S, either you have in the first step, either you have to replace it by S1 or you have to replace it by S2. And then from S1 or S2 you derive some string. But if you derive something from S1, since we are taking all the production of this first grammar, so from this part onward it is just same as this grammar, right? So this W has to be a string in L1. Similarly, this has to be starting from S2, so this has to be a string in L2. So if you are deriving anything from S, then it has to be a string either in L1 or L2. So that is why this holds. Similarly, for concatenation, again we take the variables of both these things. We take a new start symbol. We take all the productions from here and here. So this thing. And this is a new start symbol. And again we just introduce one more production. So this is just one production. And again, and when is some string in this L of this G? So starting from S you have to derive this string, and from S the only production that you can apply is this. So S goes to S1, S2, and then this S1 has to expand into something, and then this S2 has to expand into something, right? And in this part, once you are in S1 and S2, you never encounter this capital S again. So all the productions for this S1 are from this P1, and all the productions you apply for expanding this S2 is in P2. So these are again just the derivations in G1 and G2. So that is why this, if this x1 expands into say W1 here, and if this S2 expands into this W2, so here, so this means that this W1 will be in L1 and W2 will be in L2. So that is why this W, this is a concatenation of two strings, where this is in L1, this is in L2, and this happens for all the strings in LG. So LG is precisely concatenation of L1 and L2. Okay. So then we come to clean closure. So if L is a CFL, then the clean closure of L is also CFL. So again, we consider the CFG for this L. So okay, let's call this G prime. Okay, let's call this G prime. And so this is also G prime. So what is this G prime? This G prime is just G again. So it's taking all this V, all this P, but it introduces a new start symbol again, say S prime. And so this is the new start symbol, S prime. And it has this two production for S prime. So S prime can go to S prime S or epsilon, where this S is the start symbol, it was the start symbol here, is right. So now again, when can some W be in this G prime? So let me just so I'm talking about G prime here, G prime here. So okay, so when can this be generated by G prime? So it can happen if and only if you can derive this W from this S prime. And when you are starting from this S prime, so just consider a leftmost derivation. Okay, so if you have any derivation, you also have a leftmost derivation, and vice versa. So from here, how can the leftmost derivation proceed? So you have to expand this, and the only way to expand this is this, right? So either you can go to epsilon, so in that case it's fine, epsilon is in L star, or you have to apply this. So if you apply this, you get S prime S. So at this point you can apply also epsilon, so then you will only get S, or you will apply this S prime S once more, so you will get S prime S square. And in this fashion, if you apply this part, this S prime S I many times, so you will reach this S prime S I, right? And then finally you have to apply this epsilon, otherwise you won't be able to get rid of this S prime. So in order to get rid of this S prime, eventually you will have to apply this this epsilon. So we get S to the I, and from here each of this S has to be expanded into some terminals, right? So each of this S I is each of this S in this I many copies of S, so that expands into some Wj, okay, where all this Wj are expanded from S. So that means all these Wj's are part of what? This language. Okay. So language generated by this grammar. So that means this part that you see, so this continuation is this is in say L to the I, but this happens for all I, right? So for any I, you can have concatenation of this W1 up to Wi, where each Wj is in Lg. So that is why you can have all the strings of L star, and vice versa also. If you have something in L star, that has to be of this form, and that can be derived from here. So any string in L star will also be in also be generated by this grammar G prime. So yeah, this is a grammar for L star. And then we will prove this statement. Okay. So for regular language, we proved that if say L1 is regular, sorry. So we proved that if say L1 is regular, say this is regular, and also if L2 is regular, okay, so then their intersection is also regular, right? So this we proved for closure when we proved closure for regular language. So what about the CFL? Can we say the same thing about CFL? Like if this is say CFL and if this is CFL, both are context free. So can we say that their intersection is also CFL? So we can't say that. We will prove that CFLs are not closed under intersection. But what we can say is, so if you have a CFL in one hand, okay, and if you have a regular language as the second part, okay, so if you take intersection between this, so one is CFL, another is regular, so then you get a CFL. Okay, so CFL intersection CFL is not a CFL, but CFL intersection regular is a CFL. So this is what we are now going to prove. And for that, let's just go back and try to remember how we proved that this intersection of regular to regular was regular. So one proof for this thing was using product automata. So if you forgot that part, you can go back to the closure of regular languages and look for the product automata there. But it was very simple. So given to say DFA, okay, with their different set of states and different transition function. So these are the two different transition functions. So we just constructed a product automata where the set of states is now the product of this Q and P. So it's a pair where the first part is from here and the second part is from here. And the transition, so from one pair of states, you will go to another pair of states here, right? So because here the pair itself is the one state, right? And how was this done? So it was simply I'm putting two transitions together. So if you have a transition, say here in M1, so this is this delta Q, and this is Q from here, this capital Q. So if you have a transition like this in M1, and if you have a transition like this in M2, where this P is going to pre prime on the same symbol, okay, so the input symbol is same here. So then these two separate things can just be simulated by just one step here, where we are going from PQ to Q prime P prime on this same input symbol A. So that means if we have a transition of this form, say this Q is going to Q prime on A and P is going to P prime on A. This happens in M1 and this happens in M2. So then we just put this together in a single transition in M. So in M, again, the states are product, the pairs of states in here and here. So this QP is going to Q prime and P prime on A. So that was the idea. And once you have that, you can do it for multiple steps. So if you are starting from the start state of M1 and M2, so and if you reach two states where both of these are say final states respectively in this M1 and M2, so then you know that this string that you processed, so that is in the language of M1 also, and that is in the language of M2 also, and that is simulated by this one path in M. So this will be in the intersection of L1 and L2. So that was the idea for regular intersection regular. So we can carry forward the same idea in PDA intersection regular. So in PDA, so you just take say one PDA. So now this M1 is no longer a DFA, so this is a PDA. So this has some state, this stack symbols, its transition, start state, start symbol, and final states. And this part is a DFA. Okay, so this is a PDA, but this is a DFA. So this has states, this input alphabet, and transition function, start state and final state, right? And here again the idea is same, that if you have a transition here in M1, okay, on say some symbol A, and again if you have some transition here on some input, the same input symbol A, right, this two A's are same. So we have to somehow simulate both these transitions in one transition in some PDA that we construct here. So how can we do that? So in this PDA, again, the states here should be the pairs of state, where the first part of this pair is coming from here, the second part of this pair is coming from here. So the state space is this. So the set of state is this Q, again, Q product P. Okay, and then what happens? So it goes to Q prime P prime as before on A. Now, but what this has to do something with the stack also, right? But here only this part has a stack, because this is a PDA, this is a DFA. So this does not have a stack. So this is for this M2, which is a DFA. Only this M1 has a stack. So whatever it does to the stack, so it just replaces this symbol Z with gamma. So this also does the same thing. So this will maintain the stack in the same way that this maintains the stack. Okay. So the moves of both this PD and M2 are simulated. These two moves on the same symbol is simulated by this single transition here, where the change of state is from QP to Q prime P prime, like this, and the action on the stack is also same, but then here only we had one stack, and that one here also we have the one stack, and the stack are operated in the same way. So if we write it down as an equation, so this is what it looks like. So if we have in the PDA, say we are going from state Q to Q prime on input symbol A, and sorry, this should be gamma. This should be gamma. So this is gamma. Okay. This should be gamma. So if we have this, and we are replacing this Z by this gamma in the PDA, and in the DFA, suppose we are just going from P to P prime on A, so then we just club these two transitions as this one. And see, the PDA is non-deterministic, so that is why I cannot put a equal here. So I am just saying that this is one transition in the PDA, and this is one transition in the DFA. So if these are two transition in this two machines, then in the product machine, the product PDA, we have this transition where this QP is going to Q prime P prime. And sorry, again, I should have a comma Z here. I should have a comma Z here, right? So this has to have three components, and this Z is not here, sorry. Yeah. So this is the state. So please make this correction. So this is the state here, because it comes from q times p. So this is the new state, q prime p prime, which again comes from q cross p. This is the current symbol that it's processing, because it's the same here and here, here and here. And then also it says the stop stack symbol z, and it replaces this z by gamma and moves from this state to this state. Okay, so this one move will simultaneously simulate these two moves. Okay, and similar to the previous slide, where we can now use induction on say a length of string to show that it simulates the action of these two machines on this one machine. So we can do the same thing. So this gives you a transition for single step, right? So now we can use induction on say more than one step, so on I, so that we can show that this happens, that you start from some q and p and you process some string w. So this has length, this can have length more than one, and suppose the stack was alpha. So this goes to q prime p prime, and the input is completely exhausted. So all the input symbols are processed, so nothing is remaining, and the stack is now beta. So this happens if and only if separately this happens. So separately this happens means this q goes to q prime, this w is completely processed, and this alpha goes to beta. So this is just for m1. So this happens in m2, in m, right? So this happens in m, and this happens in m1, and this happens in the DFA, because it starts from p, it processes this entire w. That is why we have a hat here. So we are using extended transition function here, and after processing all of this, it goes to this p prime. So again, this and this, so these two separate paths are simulated by just this one path in the product PDA M. So now we can, if we start with the start state of this both machines, so this q and p, if we take as q0 p0, where we have this q0 and p0 here, start states, and this alpha, if we take just z0, which is the start symbol here, so this is the initial configuration of the stack, and we process some w, where this w is completely exhausted, and this q prime p prime, we reach q prime p prime after I many steps, and the stack is something. So this happens if and only if separately this happens, that starting from q0 after processing w, and starting from this initial stack symbol, it goes to this q prime after exhausting all the inputs, and the stack goes to beta. And here, if this starting from this p0 after consuming this whole w, it goes to p prime, right? So, and now you see that so you consider acceptance by final state in this PDA and also in this PDA. In both this PDA, you consider acceptance by final state. So you see that so this w will be accepted here if this q prime is a final state in the PDA. So this will be accepted in the DFA if this p prime is a final state in the DFA, right? So this w is separately accepted both in the language of this m1 and in the language of this m2, if and only if it is accepted here, because this is what, so this is what the final state is. So here the state of final state is this, you see. So a pair of state is a final state here if both the components here and here are final states, right? So from here, after consuming this w, you can reach a final state if and only if separately after consuming w, you can reach a final state in both m1 and m2, and starting from this start state, and this is also a start state. Yeah, so this is the start state of this M1, right? So that is why it ensures that the language accepted by this product, PTA, is in fact the intersection of the language accepted by M1 and M2. And for this M and M1, we are talking about the language accepted by final state. So that is why it is L of M and L of M1. For DFA, that is only one thing to do. So yeah, we have proved this part then. Okay. Now let us prove that CFLs do not have certain closure properties that regular languages have. So in particular, we will prove that CFLs are not closed under intersection, and it's not closed under inversion, right? So for that we just need to give examples, right? Counter examples. So here the example that we consider are these two languages, L1 and L2, so that their intersection is this language, okay? A to the I, B to the I, C to the I. And we have proved, so when we proved pumping lemma for CFL, so using pumping lemma for CFL, we proved that this language is not a CFL, okay? So we know that if we can construct this L1, L2 where their intersection is this one, so then we have proved that this intersection of two CFL is not a CFL. But what are this L1 and L2? So here you see that all these powers are equal. So this L1, I take this two powers to be equal, this AI, BI, so this I is same, but then this C to the J can be anything. So J can be less than I, J can be greater than I, J can be equal to I do not care. And similarly here these two indices are same, so this BJ, CJ, so this J is same for this this thing, and this I can be anything, so A to the I, this I can be less than, equal to, or greater than J. So if I take intersection of these two, so it will ensure that the indices here and here are same, and this will ensure that the indices here and here are same, so all these indices will be same. And how can we show that these are separately CFLs? This is easy. You see that this part is just the classic CFL, A to the I, B to the I, and then you are just concatenating that with C star. Okay, so if you need the grammar explicitly, so this is the grammar. So this is just concatenation of these two things. Okay, but this A part is just, you see that it's generating AI, BI. So we have seen this many times. And then this capital C part is just generating C star, so it's CC, and so the only type of string it will generate is C to the J. So in fact it generates everything precisely from C star. It generates everything precisely from this A to the AI, BI for all I. And this is concatenation of this part. And this is same where this A is now just generating, say, this everything from A star, okay, using this production, and the C is now taking care of this BJ, CJ. So again, this is just same as this one, and you know that this we have seen many times. So this generates this BJ, CJ, and this is the concatenation of this thing. So these two are separately CFLs, but the intersection is not a CFL. And the non-closure under intersection will actually imply that it is also not closed under inversion, because you see that if CFLs are closed under intersection, and since we have already proved that CFLs are closed under union, so these two things, that closure under union and closure under inversion, will imply that CFLs must be closed under intersection. But since we have proved that CFLs are not closed under intersection, and we have proved that it is closed under union, so then it cannot be closed under intersection. So you see, because of this relation, right? So if you see intersection of L1 and L2, so suppose L1 and L2 are CFLs, right? So this I can write as inverting and then again inverting. So this is identity that holds for any language. So inversion of inversion is the original language. And then this part, this L1 intersection L2 and inversion of that, just this one inversion. So by by set theory, it's just this inversion of this union inversion of this. Now if CFLs are closed under inversion, so then that will mean that since L1 is CFL, so this L1 bar is a CFL, and since L2 is a CFL, then L2 bar will be a CFL if it is closed under inversion. Okay, and then their union will also be a CFL, and since this union is a CFL, then their inversion will also be a CFL if CFLs are closed under inversion. So then that means if CFLs are closed under inversion, then this whole thing, which is this, will also be a CFL for any CFL L1 and L2. So if we take any two CFL L1 and L2, then this will mean that their intersection will be a CFL, but which is not the case, which we have proved here, right? So we have a contradiction here. So that is why we cannot assume, so it's false that CFLs are closed under inversion. Okay. Next we come to substitution for CFL. Okay, we have already seen substitution for regular language. So now we are considering for CFL. And it is almost same as substitution for regular language. So what was substitution for regular language? So it is just a map from a string over some alphabet, say sigma, where a string is mapped to a language over some other alphabet. Okay, so a string is being mapped to a language, and so this is how you map a string, and then you extend this map. So instead of a string, if you take a language over this alphabet sigma, so then f of L is what? So it's a union of all this FW, because each of this FW is a language over this alphabet. So we take the union over all these languages where this W is coming from this L. Okay, so this is how we define f of L, and this map should satisfy this property that f of xa is f of x concatenated with f of a, right? So this is a string, this is a symbol. Okay, so this a is a symbol, this x is a string over this. And the only difference from this substitution over regular language and substitution over CFL is that for a symbol, okay, for all symbol a in sigma, this f of a, for the regular language this was a regular language. Now for CFL this is a context-free language. Okay. So again, this f is a map which maps strings over this sigma to some language over delta, such that if you take a single symbol here, f of a, so that is a context-free language over this delta, and it also satisfies this condition that f of x a is f of x concatenate with f of a. And then we define f of L, where this L is a language over sigma, as a union of all this fw, where this w is coming from this L, right? So this is what the definition for substitution for CFL. And we will show that regular language, CFLs are closed under substitution for CFL, right? So we will show that if this L is a CFL, then this f of L is also a CFL. And this part, if you just expand it over all the symbols, because you have a symbol here, then this x can also be broken down into its last symbol and the remaining part, and you can recursively break it down into all symbols. So then it will look like this. So this f of a1 up to n, so this will be the concatenation of f of a1 dot 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 f of a n, right? So f of n, and this dot 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 means this thing, because for each of this f of ai it will map to some rai, right? So one example will be this. So you take a context-free language, this L, say AIBI, and suppose you have some RA and some RB. So this RA and RB are CFL. So I'm not specifying what RA and RB is. It works for all CFLs, RA, RB. But you see this is what it is. So then what will be f of L? So f of L will be so this union of this thing, right? Because if you map just this single string, so this W, if you map, so this is RA to the I, RB to the I. So this is a language, right, in itself. And then you take the union over all these things and it will look like this, right? So what is RA to the I? So it is just some concatenation of I many strings, where each of these strings, this xj, so this is coming from RA, and then it is followed by this RB to the I. So again I many strings, where each of the strings, say yj, so it is coming from RB. So this is what it looks like if I completely break it down over RA and RB. So that's what it is. Now, in order to prove that L is CFL implies FL is CFL, let's just proceed with this example, and that will make it clear for what happens in the general case. So, in this example, you see, as I explained, it looks like this. So, you see that each of this A here is replaced by some string in A, as this array, right? Yeah. So each of this A here is being replaced by some string in array, and each of this B is being replaced by some string in RB, right? So what we can do is we can take the grammars of this RA and RB. So it has variables VA and VB and productions PA and PB, start symbol SA and SB, and so on. And this is over delta, right? Because this RAs are languages over delta. So okay, so this V should come here and delta should go here, because we take VTPS. Okay, just that's a trivial thing. So you just remember that here this is the terminal. This first part is the terminal. This is the variables, and we can assume that the variables are disjoint. So again, without changing the language, we can always rename the variables. So without loss of generality, we assume that this VA and VB are disjoint. So that means this SA and SA are also cannot be same. And the strings here, so what are these strings? So these are from this language array. So that means it's an array if and only if it can be derived from this SA, the start symbol here, and again, so this will be in RB if and only if it can be derived from this SP, start symbol here, right? And here you see that the grammar for AIBI is this, right? S goes to ASB or epsilon. So this means that this generates this grammar. So it's the grammar for this L, not FL. Now this AI should be replaced by, so each of this A should be replaced by one of this XJs, and each of this B should be replaced by one of this YJs. So what we can do is, instead of generating AIBI, we can just change this AB to say SASB. So SASB was here and here, right? The start symbol of here. So now instead of generating strings like AIBI, it will now generate strings SAI SBI, right? Okay. and then each of this SA will be expanded into some xj. So this SA will be expanded into some xj. So this has a star here, and this has a star here. Okay. So yeah, each of this SA will be expanded into some xj, and each of this SB will expand it into some yj. So that is why you will have this I many xj's and I many yj's followed by this, and it's the same thing. So what is the idea here? So the idea here is whatever language you take here, it has some alphabet. This alphabet is sigma, right? And whatever alphabet you have here, we are taking the production for this language L, and we are replacing the productions. So each symbol is being replaced by the start symbol to correspond for the corresponding language. So for this A, the corresponding language was RA. So this A was replaced by the start symbol of RA, which is SA, right? So that means whatever string that we were generating for L, so we will use, we will generate the same form of string, but now this A will be replaced by SA. Similarly, this B will be replaced by SP. So this happens for any language here. If I take any language here, and if I replace the productions here, so if I replace A and B in the productions here with SA and SB here with the productions here, so then whatever string we are generating for this language L, so we will use generate the same form of sentential form, but AB will be replaced by SA and SB. Then this SA and SB will be expanded like this, because we have the productions for this and the production for this also. So this has this product. So the modified production for this L1. So this part comes from this L, and then it also has the productions of this and this. So once we have the sentential form, which consists only of the start symbol of this, so then we can expand it into according to this production and this production. So that means the general strategy is this, that you have the sigma where the symbols are A1 up to AN, say, and you have the corresponding grammar. Okay, for RAI you have this grammar with start symbol SAI, right? So this belongs to RAI if and only if it can be derived from this SAI. And then you have the grammar for L. So this L. So the grammar for this L with start symbol S, right? And here you have some production P. Now all production in this P, so the symbol AI is replaced by SAI, right? So this is what we did. So here for this AI, A to the I, B to the I, we replaced it like that. So this happens for any general L, right? So here the productions are modified, like where this symbol AI is replaced by the start symbol corresponding to this thing. So that means in this L, if you can derive this string, so AI1 up to AIK, if you can do this with this production. So since here this AI is being replaced by SAI, so if you can derive something here, then you will derive the corresponding sentential form here, where instead of AI you have this SAI, right? And then from each of this start symbol, since we have all the production of this thing for each SAI, we have all the corresponding productions here, this PAI. So from each of this SAI, you will generate some XJ, right, which is in RAJ, right? So this will be the concatenation of this thing, and the language, this will be the union of all these things. And this is precisely this f of L, right? And then for Regular language also, we mentioned that homomorphism is a special case of substitution where this when you are mapping this string, so it's not just for one symbol. When you are mapping a string, so it is, the image is a singleton. So here if you see, so in the previous case, so if this is a string, so then this is a set of strings. So this is a language. So this was a set of string over this delta, right? Yeah. So for substitution, you see that when you are mapping a string, it is mapping to a set of strings. So it's a language, so which is a set of string over delta. But for homomorphism, this maps to a single string. So you can say it's a special case in the sense that the language is a singleton set. So we do not think of this as a language or a set. So we just take it as a map from a single string to a single string. Okay. So h of this string is a string over this delta. So the map is now from sigma star to delta star. So again, this comes from the substitution part, that if you take h of xy, then this is h of x into h of y, and this is the reason we call it homomorphism. And this means that again we can break down this part in all its symbols. So then if we recursively apply this thing, we see that this is actually the concatenation of A1, HA2, H up to HAN, right? So this is important. But as I said, since this is a special case of substitution where the language is for each of the symbol is a singleton, which we in fact write not as a language but just as a string. So it is clear from the previous proof that CFLs are also closed under homomorphism, and here the construction, if you see this construction, so here we were replacing this AI with the start symbol and then again including all the productions for this RAI. So here the construction will be much simpler. So we just replace, we just take the productions for this L. So again, what is L? So H of L. So H of L. So once we have defined this H of W, so this H of L is nothing but the union of all the H of W. So in this case, we can just take this H of W, right, where this W is coming from L. So okay. So this is what H of L is, and so the grammar for H of L is what? So if we just replace this AI by this H of AI, just because of this, so you see that when you are taking this H, just this AI is being replaced by H of AI, right? So if we just do that in all the productions, then whatever string we derive, for that also we will have this thing.